Okay, so we left off talking about mercury and nitrogen and how those energy levels, when they're moving, those energy levels are going to emit color. And so notice that as the electrons lose energy, right, by emitting light. So what they do is they get excited out into these outer levels, these outer quantums, if you will, right? And then as they lose energy, right, they will emit light. In fact, that's how they emit light, is by losing energy. So that light, the blue that you see, the pink that you see, right, the blue here that you see with the mercury, the pink that you see over here with the nitrogen, that means that they are actually losing energy. And so they're going to be returning to lower energy levels. And so that's important. Valence electrons, right? Electrons are what cause all of this to occur. And so we can look at certain fingerprints of certain atoms. So you look here, you've got copper, which is always sort of this green hue to it, kind of yellow-green bands. Barium is more of a yellow, almost white. Potassium, which we've done in class before, is very bright and kind of that almost pure white. And then you've got strontium up the top, which always burns more of a pinkish red. So very important to note that we can in fact look and identify some of these elements by the colors that they give off as they are returning back to ground states, right? They're losing energy. So what about when atoms absorb energy? Electrons then will move into higher energy levels. These electrons then lose the energy by emitting light, as we've said, and they're going to return to their lower energy level, much like you and I would return home at the end of our school day. So Bohr came along, and Bohr model said that the lone electron in the hydrogen atom can have only certain specific energies. When the electron is at its lowest possible energy, that's what we term ground state, right? That's your ground state. Excitation means it's going to get excited, right, of that electron by absorbing energy, will raise the atom from the ground state to what we call our excited state. So we're just kind of summarizing here what we've been talking about. Important to note those. And then our quantum of energy in the form of light is emitted when the electron drops back to a lower energy level. So again, we're seeing that light, as it drops back down, is actually losing, right? That atom is actually losing energy to emit light to go back down to a lower energy level. Sometimes it'll go all the way back down to its ground state. Other times it will stop at a particular lower state. So it may go from level 3 to level 2, right? It may not go all the way back down to level 1 and so on. The light emitted by an electron moving from a higher to lower energy level has a frequency. We talked about that earlier as well. And it's directly proportional to the energy change of the electron. So that's the distance that it's going to be traveling. Will it go from 3 to 2 or 3 to 1, right? That's proportional to that. And so the three groups of lines in the hydrogen spectrum correspond to the transition of the electrons from higher energy levels to lower energy levels, right? And so you can see that frequency here in hertz. You've got what we call UV light, right, which is in this band or this spectrum right here. And we've got what we call the visible, right, the Balmer series or visible portion. This is what you and I can see with the naked eye, right, and it is in this band. And then we've got what we call infrared. And so some of you all have seen the infrared before, right? And it is in the outermost band, the most excited. So if you look here, it corresponds proportionally. UV means it's in ground state. It's as close as it's going to get to the nucleus, UV light. We excite it up a level, then we get visible light. So the light that we actually see from day to day is actually visible to us because it's excited, right? It's a little bit excited. And so it's up in the second level here. And then if we see infrared series, right, which I know all of you have seen infrared cameras before, or examples on TV, then they're excited another time, right? And so they're out at the third level here for infrared. But this band will continue to push on as we go out layer after layer here of the bands of excitement. So that's important to note as well. And so what we get here is you can see now in this model does a really good job of explaining. There are up to 7 levels or layers, if you will, of excitement that electrons can attain. So they can go from all the way from 1, right, which is closest to that nucleus, and they can come out to level 1, 2, 3, 4, all the way back here to 7, right? And notice the higher levels they go, the further away from the nucleus they are. And also that these levels will actually kind of get a little bit closer as we pursue out, right? Doesn't really show it in this diagram, but that does occur. So Rutherford and Bohr's model focused on describing the path of the electron around the nucleus, much like a particle of a small baseball, right? Then we talked about Schrodinger treating them as a wave, and the modern description of the electrons and atoms is what we call the quantum mechanical model. Comes from Schrodinger's equation, right? And so you've got the equation down here. Not going to have you do anything with that right now. Just need to know that it exists and that Schrodinger is the one that developed it, right? And do need to know about the quantum mechanical model, right? And that goes along with Schrodinger. So that's important. We're going to just skip through the slide here. One thing that's neat to note here is about an airplane. The propeller blade has the same probability of being anywhere in the blurry region, but you cannot tell its exact location at any instance. Same thing as we see to the electron cloud model, right, with the electrons. So the quantum model determines the allowed energies of an electron can have and how likely it is to find the electron in various locations around the nucleus. Again, it's going to move as soon as we say it's any direct place, right? So if we say it's right here, it's going to already move and be past that. So if it was right here on the plane's propeller, by the time it took to point to it, it's already moved over here somewhere, right? So we're using probability, right? Hopefully in mathematics, somewhere you've had some probability. That's important. The probability of finding an electron within a certain volume of space surrounding the nucleus is represented over here by the fuzzy cloud, right? We call this the electron cloud, right? So we've got our nucleus, which we said was filled with, let you fill in the blanks, right? We said we're filled with protons and neutrons, right? And then you've got this cloud model, which is out here. So all of the electrons exist out away from that nucleus, right? And the further you go from the nucleus out, the higher the energy level, the more excited that they're going to be, right? So the fuzzy cloud, an atomic orbital, is often thought of as a region of space in which there is a high probability of finding an electron. So again, we're back to the probability. We're not guaranteeing that we're going to find an electron because they continually move, and they move very quickly, right? Faster than you can blink, they've already made several hundred revolutions around the nucleus, right? It's hard to believe, but that's how quick they move. So what we got then is density maps, right? And we sort of create these boundaries. You see our nucleus is solid there in the middle, and we'll create these boundaries, and we will create different layers, if you will, sort of like an onion, right? And so we're going to look at those energy levels. Orbital is a region of space in which there's 90% probability, right? That's like I said, there's no guarantee, but we have a 90% probability of finding an electron in that orbital region. Now orbitals can take different shapes, right? So we're going to start looking at some of the orbital shapes. Now we know that there's 90% chance of finding an electron in this orbital region. But they also have different shapes. So the very first one we see is called the s orbital, and it is spherically shaped. It's a big circle or sphere, if you will, right? A smaller atom has fewer electrons. It's going to take up less space, and the larger atoms will take up more electrons and have more space, right? But our first one that we encounter is a spherical shape. So if we're down at level 1, you're going to see 1s, right? Which means level 1, and it's a sphere. It's a circle, right? Sphere, three-dimensional circle. Level 2 would move on, and it would be first a sphere, right? So you'd have 2s. So if we were looking, you'd have 1s and then you move to 2s. And we're going to actually go through this practice together. Once you get past the s's, then you start seeing what we call the p orbitals, and they are dumbbell shaped, what I like to call actually a figure eight. So if you were to trace this and think about a figure eight shape, that's exactly what the p orbitals are. They are figure eights, right? Some people call them dumbbells. I like to think of them as figure eights, but you can do either, right? And it can move along different axes. So it could be up and down, it could be left to right, it can move the other direction, right? But it can move in a three-dimensional, because we're dealing with three-dimensional objects here. They are not just a flat piece of paper. P orbitals can also exist together. You can have all three of those arranged together, which you see, right? You've got the one figure eight that's going up and down. You've got one figure eight that's going transversely, right? And the other figure eight is moving cross horizontally, right? But they're all figure eights or dumbbells, and they can all exist at the same time even. So that's pretty unique. So here you see you got the s orbitals, which are spherical. You've got the p orbitals, which is our dumbbell or figure eights, right? You've got d orbitals, right, which is a pair of figure eights or two dumbbells, right? And then you can have f orbitals, right? And f orbitals are also figure eights, but then they've got these rings. If you look back up here at the last one of part D, you can have this ring that goes around the center, right? And same thing here, except with the f's, you got a ring at the top and a ring at the bottom. The main thing is just want you to know the basic shapes, but you don't have to worry about being specific here, drawing each of these out. But I do need you to know that S's are spherical, P's are dumbbell or figure eight, D are multiple dumbbells or figure eights, and F's, right, are even more. So there are different levels and different quantities that we're going to talk about here, but you do need to take away from this slide specifically, there is S orbitals, there are P orbitals, there are D orbitals, and there are F orbitals. We're going to do something with this, so please make note of that. Not particularly interested that you know the three-dimension shapes, but you do need to know that S, P, D, and F are there, and they are useful to us. So if you look here, this does a good job. What we call these are shells, right? Shells of an atom contain a number of stacked orbitals. And so we can start way down here at the bottom. Level 1 is just sphere, 1s. That's all it can be. If we move up an energy level, then we get to 2s, which stands for 2 spherical, and then we get to 2p, right? Then we move up to 3. You can have 3s and 3p, right? You get to 4. Well, you can have 4s, right, and 4p, right? And then we're going to also get into d's and f's. We'll talk about that more as we move forward. First and second level, we said, were just straight s's, and once you enter level 2, you start to look at p orbitals. And there's a whole flow chart and diagram that I'll give you with this, but if you really wanted to pinpoint it, there it goes. 1s is closer to the center, 2s pulls out a level, and then you've got the 2p's coming out of that as well. So why are atoms spherical? Well, different atomic orbitals are denoted by letters. So you've got all this. We'll talk about more about this in class, because there's actually a flow chart that we're going to use. But if you look here, it's kind of interesting. Energy level 1 has one sublevel. It's S, spherical, right? Has one orbital, right? And it can hold 2 electrons. So the total electrons in a energy level of 1 could only be 2. But then we move to level 2, right? Now you can have 2 sublevels, which is an S and a P. The S can hold 1 pair, and the P can hold 3 pair. So 1 pair is 2, 3 pair is 6. Then we get a total number of 8 electrons in our energy level. And so on and so forth. We'll pick up here in our next segment. The recording device that I'm using will allow me to record in 15-minute increments only. So everything will be kind of broken down into 15 minutes at a time. Hopefully these are valuable to you. I know a lot of you that have been missing class. This is a good way for you to still hear lecture without being physically present in class. Well, let me know your feedback. Thanks.